Turan in England. Hello.
Oh, hello, good morning. I'm here with ClipperCab. And yes, it turns out we've been mainly doing BMS related topics, and I guess we'll have Janos explain what the issue was.
Alright. The problem with the previous BMS, this is a 40 kWh BMS from the Nissan Leaf pack, and we've got the 96 cell tabs here, we've got the individual balancing chips, and then there's a micro on the other side of it. The problem with the setup that we have here is that we've got, instead of one battery box that you've got in the Nissan Leaf, you've got two battery boxes, one in the front and one in the boot. So we had to extend half of these wires, and I posted about this in the forum before. We ended up getting interference problems where everything works fine and then the BMS reports fine values and all the salve voltages are fine, until you put your foot on the throttle and the inverter starts working. And we tried to mitigate that with many different solutions. We tried rerouting the sensing wires, we tried rerouting the high voltage wires, we tried different BMSs in different vehicles, and sometimes it did work for a period of time, but it was never quite clear why it worked and why it didn't work. Which is why then we thought, let's be more radical and try a new solution, which Johannes is going to talk about.
Good. So coincidentally, while I was in Sweden, I started developing a new form of BMS. And that's what I got here. It's a 16-channel module, and this means we can distribute it between the front and the back. So each module is going to sit really close to the cells it's monitoring, and is therefore very unlikely to catch any sort of MI noise or whatever noise might be in the car. So I thought this was the ideal chance to combine some work at ClipperCab with some open inverter work, testing this BMS for the first time in a real car. Now what we see here is a cascade of 3 of these boards that will go into the front of the car, and Harris over there has prepared it so it interfaces one-to-one with the existing Nissan cell voltage harness. What do you call it? And yes, while we're here, we can briefly talk about how this is being cascaded. So what we see here is the power supply, the blue and the red, and then there's an enable line, which would be connected to your charging signal or your ignition. And then here for data exchange, we've got a CAN bus, and all these jump from module to module just in parallel, except the enable signal, which is being propagated in a daisy chain manner. We first switch on the first module, that switches on the second module, assigns it its address, and then that switches on the next module, assigns it its address. So then we've automatically made sure that they all have a unique address that they work with. Right, so another feature of a BMS is to measure the current. It's currently being put in or drawn out of the battery, and also to measure its temperatures. And that's why each module has 2 temperature sensor inputs and 1 current sensor input. And you don't have to use it, you can use it, and just use the module that's closest to the respective sensor to read it. Right, so we have been testing this on this half Nissan pack right here. We've got the high voltage tabs here, and we've got the low voltage connector here, which we're also reusing to a plug and play solution. And as with every good project start, we have burned quite a lot of silicon. And I'm just going to go into why that happened. Okay, so these many ICs here is the max control, and that is responsible for switching a pair of MOSFETs on. As with every power electronics, like between changing channels, we need a bit of dead time. Like we turn everything off, and we change channels and turn everything back on. Now, the way we do this is we've got a so-called shift register. And we've got an isolator here with 2 channels, and that transports a clock and a data signal to the shift register, and that then has parallel outputs that control the circuitry that comes after that. let's look into how the shift register works and what the principle is here. So on top here we have our channel selection signal. That's comprised of 4 bits because we've got 16 channels. Then 1 bit is used as an enable signal. So if that is low, no MOSFET is switched on at all, and if it's high, then the selected MOSFETs are turned on. Now there's a D7 dash signal, and that means that we have to go into the shift register details actually to understand that. So the long chip here is the shift register called 74HC595, and here is the shifty bit, which is not visible from outside. So you've got your data here, and I haven't added the clock to keep complexity down and the clock signal. And whenever there's a clock, all the data that's already in there is shifted 1 over to the right, and the new data is being shifted here into the first bit. And eventually you filled it up with your 8-bit of data. And then there's another control signal, it's called a latch signal, that latches the shifted data to the output registers. Now normally this latch signal is another 3rd control signal, but our isolator is only 2 channels. So I used the 8th or the 7th data bit, however you count, which is visible from outside the chip, called D7 dash. It comes directly from the shift register. And so once we get a 1 in the last bit here, we automatically latch the entire thing to the outputs and then control the mux with it. Now the thing is, if we completed that once, that's fine, but at some point we're going to change channels and we're going to keep on shifting. There's going to be some random data in here, and we're going to shift it through, and then every now and then a 1 is going to end up in this latch register, let's call it that. And we're going to shift out some random control signals here that we don't really want. To mitigate that, there is a 4th signal, a reset signal, which I've drawn in pink. And we want to trigger that before putting in a new word. And it's important to note that the reset signal only resets the internal shift register and not the output registers. So these are unaffected by the reset signal. Going back to the timing diagram, here is our D7 dash signal. And with some delay, it triggers the reset signal. So right after we've shifted the data in and latched it to the output registers, we reset the shift register. Get rid of everything, reset it all back to 0. The way this is done is quite simplistic. This 10K resistor is connected. You can just draw this connection. This connects here. So it goes through the 10K resistor into the MOSFET, and that then pulls down the reset signal, which is held high normally by a 1K resistor. And because this MOSFET has got some internal capacitance, it forms a RC low pass with this resistor here, and that is what creates our delay. And probably this capacitor adds some delay as well. Now it turns out that in some boards, down to whatever reason, this reset signal is not generated properly or not generated at all. And at first you'd think that isn't a problem, but it is one because it eliminates our dead time, or 0 here, that we want between switching the channels. Yeah, so say we switch from channel 8 over to 7, and then somewhere in between channel 0 is going to switch on, and we got a bus collision, you could say, and it ends up with actually burnt MOSFETs and burnt PCB tracks. That's what we're up against today. Once that is fixed, I do expect this to work just fine. Let's see. Hey Janusz, what's happening here?
Right, so we're testing your new flying ADC board, and we did release some smoke earlier, and we thought we found it, or you thought you found the issue, and then put it back in and release smoke again. So we're now trying to figure out divide and conquer which where the problem might lie. One difference that you identified, you tested these a lot in Sweden, and one difference that you identified is that this is the first time you're cascading or using multiple boards together instead of having a single board next to the, connected to a battery. And for the output channels, so for the gates, for the individual FETs here, you notice that it's always the Q5 FET that pops. So what we've done now is, and for Q5, you had Q5 and Q6 here, or empty there, in two in series, but they weren't rated high enough. So we now found another one that is rated for 100 volts, and we jerry-rigged that in. And what I'm doing now is we noticed that we released the smoke always like after a minute or so of turning it on outside, and the only thing that could be different there is like connector position, but we don't think that's the problem. So I'm just turning this on and off for a couple of times before we try it in the car again.
I've now returned from London, and unfortunately without a working BMS solutions. Despite all the improvements we made on the board, we could not get it to work reliably. It would just keep blowing traces or MOSFETs, but only if we used more than one module in the setup. If it's just one module, it will work fine. We can power cycle as often as we want. Not an issue. Now, so fault finding goes on. I'll just talk about a little bit about the details of the MOSFET switching here. So in principle, we have 17 inputs here. One is ground, and then one for each cell tab of the 16 cell tabs. And then the output of the MOSFETs is connected to a common output, so to speak. So the even ones, like this one, and then 2, 4, and so on, they are connected to what I call the negative output, and the odd ones, like 1, 3, and so on, are connected to the positive output. And we can actually physically see this if we turn the board around. Here's some contrast for you. So this would be the positive bus, the outer one, and this is the inner one. And what was very noticeable from the blown boards, got one here, is it's always, let's get into contrast again, it's always the negative bus that has the shorts. We never had a board, unless I did something stupid after the defect, that has burned the positive bus here. So it's always, so to speak, on the even side of things that things go wrong. That's a hint, but doesn't quite point us to the solution yet. So some more details about the switching. We see here's a row. You might be able to spot that these are smaller MOSFETs. These are N-channel MOSFETs. And then there's a row of P-channel MOSFETs and another row of P-channel MOSFETs. That's because every MOSFET has a diode inside. So if you were to use just one P-channel MOSFET, the diode would start conducting as soon as the voltage becomes more positive than the source pin here. So basically, this one would start to conduct once we switch this one on. That's why we have two P-channel MOSFETs back to back, because then one diode points one direction, the other points the other direction, and they will never conduct any current. Good. The N-channel MOSFET's only job is to switch on the P-channel MOSFETs. And the gate of the P-channel MOSFETs is held to the source by these 10K resistors here. And the gate of a P-channel MOSFET has to be pulled lower than the source for the MOSFET to turn on. And that's just what the N-channel ones do. And you probably will not be able to see this because the numbers are really small. The first 4 MOSFETs have, or gates have a 0 ohm resistor. So this one is going to be sitting at, let's say, 16 volts for a 4 volt cell voltage. So the gate source voltage will be like 16 or maybe maximum 18 volts or minus 18 volts when we turn on the MOSFET. And that's okay because the maximum rating is 20 volts. And then here we will see an increasing value of resistors, which then form a voltage divider with the pull-up resistors here to not exceed the rating of the gate source voltage. And then here on the last 4 we see an additional Zener diode, and that prevents the drain source voltage of the N-channel MOSFETs to go above like 50 volts, because these N-channel MOSFETs are only rated 60 volts to be able to stick with the cheaper parts. Right, and just to prove the point, here is 2 more defective boards, and you can see again it's the negative or the even voltage bus that has burned. Yes, a bit more context on the burns is it seems to be a power up glitch. So if you power it up and it doesn't burn, then it will just work for hours and hours and not cause any issues. But then if you do a couple of power cycles, it will actually blow up. And also, like between powering it up and the mux actually starting to work, there's like a 1 second delay caused by like the bootloader and some internal state machine and stuff. So after that delay is when the blow up happens. So it's right after power up when the mux starts working, but only if it's 2 or more modules cascaded. Really odd situation. There have been some good hints on the Open Inverter forum targeting the kind of high value resistors on here, which might cause lower turnoff. So there's a good bit more scoping and plotting to do and to, well, finally be able to fault find this. For a better understanding of the working principle, I've drawn this little diagram. So these are our MOSFET switches, just denoted as a switch. And you can see how the outputs of the even ones all connect to a common line, and the outputs of the odd one do just the same. And then they end up at a voltmeter, which is our ADC of the BMS. And you can clearly see if we were to close, say, this switch and that switch, we have a conductive path all along here, and this trace will burn in no time. And this is obviously what's happening. I will wrap up this video here. It's already much too long for my taste, and yeah, as soon as there's progress, there will be a new one. Thanks for watching, and see you next time. Bye bye.